Okay, good morning or good afternoon, wherever you find yourself. My name is Justice Moses Aheto. I'll be the one taking you through the geospatial science. I put on the video just for you to see who I am, and those who might not see me before, to at least see me. But while I start the presentation, I don't know whether I have to still keep it on or off, but we'll see how it goes. Okay, so the plan is that we'll have the theoretical session, which is basically to introduce you to geospatial data science, where we'll look at some of the elements that is critical to the area. And then the goal is also to take you through some practical session, where we have some on practical, where we try to use the art package to do some of the analysis that we can do. Because this is very introductory, not very bad, this introduction to geospatial science. There are many in-depth elements that you can only acquire through other workshops, but I will highlight those things along the line. For instance, there's a modeling part of this. Let us remember that what we'll be doing now will go into the theoretical aspect of the geospatial data science. And then when it comes to the practical part, the idea is to be able to play with geospatial data. We'll also be creating one ourselves and then mapping it, just to have that confidence that, even in our own survey, we can collect data on the geographical information and then get that into mapping and that kind of stuff. We'll cover that one. We'll also be able to download data from some other sources where we can map ourselves, and just to be sure that we are getting the tips of the mapping. And critical to this is that we want to move away from the static maps and then into the interactive web-based maps. So those are the areas where the practical will be covering. But like Professor Amaga said earlier in his presentations, the hope is that after this smaller grant that we got, we'll use just a platform to get a bigger one, so that possibly in the next training, there will be enough time. Because if you want to go into the social modeling and the mapping, at least a week or two is required to have a hands-on intensive training for you to move from the basics to the advanced level of the social modeling, where you'll be able to, just as you do in linear regression or logistic regression and other modeling first, you'll be able to model the process spatially and then map the predictions as well. Okay, that's what you normally say, that you take into account the spatial correlation in your estimation, that you use that to make predictions. Then from the prediction, you're able to develop maps of the predicted surfaces. So those ones will take a lot of time to finish. So pray for us that we get a bigger fund from our funders, especially Bill and Melinda Gates Foundation and other funders, so that we can have that intensive one on this area. So basically, that is it. I don't want to take too much of your time, so I would like to go straight into the business for the day, if that is fine. Okay. So first, the outline is what I'm presenting to you. We'll look at what the geospatial data science is. We'll look at what the geographic information system is all about. We'll look at where they need, or the need for studying something related to GIS. We'll also look at some applications of GIS in public health. Then we will look at the geospatial data types, their structure, format, and algorithm. We'll discuss this very briefly. Then how do you represent the spatial data that is in the coordinate systems form? We'll also be working on some cartographic projections in terms of having some idea about what they are all about. And then we'll also know something briefly about spatial data mining and network processing. And then spatial data types. And then we'll look at some examples of spatial data types. I'm very sure by now some of you might have had some idea about it, but we'll look at it. And then we'll move into the practical part of it. Okay, so basically the question is, what is geospatial data science? And what do we want to achieve as far as this field is concerned? So if you really want to appreciate what the geospatial data science is, just try to look at what you do in your day-to-day modeling experience, like either the simplest, which is either the linear regression model or maybe any other type of model that you have, that you're familiar with already in your field of study or area. I mean, the question is, why do you do what you wanted to do? In geospatial data science, basically, the goal is to go deeper and to extract some insights from the data that's available to you. And then there are lots of facilities and procedures available that helps us to extract geographical information and then combine that with available data to produce some reasonable results that can be used by policymakers for decision making. So in summary, we say geospatial data science actually deals with extracting of deeper insight from data by leveraging a comprehensive set of spatial algorithms or procedures and analytical methods. And we'll be looking at some of these things in the practical session, how this is actually work in practice. And if you want to let the discipline be well understood, just take it to be a technique that is available for you to extract hidden, patterns within data, make use of deep use of machine learning approaches. And then the goal is to improve predictive ability of your models, especially. That's the whole thing. The whole goal is to improve the predictive ability of your models in a special manner. Some of you might be familiar with, let's say, you're developing predictive models, maybe having an outcome that is binary or something. And then your goal is to be able to develop a model that is very, very consistent with the data. It's the same thing that we are doing over here. Just that this time around, we are taking into account the spatial dimension. That's the only thing that we are dealing with. So to make it easy, remember that in a spatial field, apart from just the mapping, we also do what we call the spatial modeling, where we set up models and then take into account some environmental or individual level covariates together with the outcome and then make predictions. And in making those predictions, we take into account the spatial information, which is the spatial correlation. So in summary, geospatial data science is simply a procedure that can enable us to unearth why things occur and why they occur there. That is basically about geospatial data science, a tool that allows us to unearth why things occur and why, or the reason behind that occurrence at those locations. That is basically what geospatial data science is all about. So this is what we'll be expecting you to do after this work. That is always, once you're working around the area of spatial data, you really wanted to identify spatially where things are occurring and the reason behind that occurrence at those geographical locations. Okay, so now moving back to the geographic information system, what exactly are they? This, I can say, this is the engine behind geospatial data science, because you can do a survey where you have a data from the survey. Then maybe during that survey, you also collect information on geographical information system, let's say location, or let's say the coordinate and then the other attributes around those coordinates. Now you needed a skill that can help you to combine these GIS information and the statistical approaches available to you so you can come up with a result that can be used to inform policy at the various locations within the study region. So GIS is very critical in the geospatial data science. So we say the geographic information system is simply a system of hardware and software that actually supports the capture, that is the gathering, the management, manipulation, analysis, and display of geographic information. That is what GIS is all about. So it's a system of hardware and software that actually supports the capture, management, manipulation, and the analysis, including the display of geographic information. And you'll be seeing some of these things in the practical session. You can also consider this to be a system that allows you to manage, analyze, and display data geographically. That is also acceptable. And basically, in geographic information system, we are basically interested in specifying data, or maybe we want to use a data that can help us to identify specific location in relation to certain features. It can be man-made or natural features. And then those features can also be associated with other elements that we call attributes. So if you have if you collect information on geographical location, either in the form of longitude and latitude, and then around the same coordinates, you gather additional information. Maybe, for instance, if the people have a health facility, or maybe, for instance, number of children who are stunted around that location, or for instance, the distribution of mosquito bed net around those locations. Those items we refer to them as attributes in spatial analysis. We call them attributes. So if you collect geographic information, then you add on other variables like what I just mentioned, number of mosquito bed net distributed around the area, or number of children stunted in the area, or prevalence of malaria in those areas that are there. All those things, we call them the attributes. So what it means is that in that case, you have the geographic information available, and they also have other attributes together with the geographic information. So if you combine these, you can use them to do some mapping stuff, and we'll be looking at those things. There are two components as far as the GIS is concerned. There are two components, very, very important. The first component, I just mentioned it in my earlier presentation. We call it a locational data. And this is the one that helps you to extract information about the location where you find yourself. Okay, the location where you find yourself. So normally, the usual longitude and the latitude, they are the ones that forms what we call the locational data. They are the one that helps us to index or identify a particular location in our work. We call that one locational data. There is another component that we call the descriptive attribute. So the locational data that you gather, there are other information that can help you to explain or describe that location. So for instance, you can have a variable like the name of the location, or like either it is a rural or urban community, or you might have a variable on stunting, or you might have a variable maybe prevalence of malaria at that location. So these are what we are calling as the descriptive attributes of the spatial location or spatial data. And then in the GIS, location of features can be specified through any spatial reference systems. And then you and I know about the Cartesian plane, which is the X and Y coordinate system, or the global latitude and the longitude system, which is also called the global positioning system. Okay, we'll be looking at each of these. These are the two main ways of representing your spatial data, either through the Cartesian X and Y plane or coordinate system, or the global positioning system through the latitude and the longitude. One thing you should note is that in the geographic information system, there's no limit on the number of geographic features and the number of descriptive fields that one can collect information on. You can collect as many as possible. As far as you have resources to support that, you can collect as many as possible. So why do we need to bother about geographic information systems in the first place? It helps us to understand how geographic location influence health outcomes. For instance, nutrition, malaria, and other health outcomes. And this is very, very, very important to epidemiological investigations. So those of you who are already in epidemiology, you appreciate the need for GIS in your work. For instance, you might want to map the distance that a patient travels from their house to the nearest health facility. And in that work, you need information on geographical data. And GIS is the only way you can do that kind of assignment. We know from literature, with no doubt that, in fact, where people reside can serve as a marker for their personal, socioeconomic, and environmental factors that could actually influence their health in terms of nutritional status and other areas like access to healthcare services. So if you live in an area where these facilities are lacking, that is access to health facilities, if they are not available for you to use, meanwhile somebody is residing in another location where the healthcare services are just in their numbers, they can just work some few minutes and have access to those things. You can't compare yourself to those people when it comes to health service delivery and access to health services. So what this is telling you and I is that depending on which location or geographical location you find yourself, your health might be influenced positively or negatively. So to be able to quantify the differences in or the inequalities in health, which can be attributable to where one resides, then you need to have a data, which is locational data, superimposed with the maybe the attribute data, so you can explain what exactly be a reason that living in certain part of the country or your location will have a positive or negative impact on your health outcomes or access to healthcare services. In doing so, the GIS is very, very fundamental to answering that question. So the bottom line is that in our part of the world, especially in Africa, the public health resources available to us to, quickly respond to our health needs are very, very limited. So what it means is that to be able to make an optimal decision in terms of where to target and to make a maximum impact with the little resource that you have to be guided. You have to be guided. And then to be guided, you need what we call localized maps that can identify communities where maybe, let's talk about prevalence of malaria in a given country among under 5 children. Definitely across the whole country, either Ghana or Sudan or Somalia or Tanzania, it might not be possible to roll out a universal intervention to address the problem of malaria prevalence among under 5 children. So what it means is that geographic information system combined with statistical modeling approaches can help you to quantify the amount of spatial variability in under 5 malaria hot prevalence across the entire country, so that the little resource you have, you can use it to target areas where the risk of a child under 5 becoming or positive to malaria is very high, so that those ones can be attended to while you wait to get resources to expand to areas where the risk is not too high at the time you were considering. So the GIS supportive mathematical modeling or scale modeling is critical in informing optimal prioritization of the limited resource that we have. So at the end of the day, the goal of geospatial data science is to provide optimum prioritization of available limited resources, especially in our setting where universal intervention is practically impossible and ineffective. So some of the applications, you can think about disease surveillance or monitoring. Example, tracking the sources of diseases and the movement of infections. For instance, during the COVID-19, all of you have seen what happened. If you read the literature, those who have undertaken some special modeling and stuff or mapping, you see them telling you that in a given country, the spread of the disease and its movement is not uniform across countries. Within countries, even there are variabilities. For instance, if you take Ghana, even within Ghana, certain communities or areas in Ghana are more prone to, the prevalence of COVID-19 compared to other parts of the country. For instance, if you look at the northern part of the country, we didn't record much of the COVID-19 infections. But if you look at the southern part, especially in Greater Accra, and also the central part, the middle belt, like Kumasi areas and stuff, you realize that a lot of cases were reported. But somebody can just say, is it because of the population or not? This is something you have to use the SCAM modeling procedure combined with the geographic information system to address. So yes, so even within countries, there are special differences in the prevalence of COVID-19 or incidence of COVID-19. Even if you go within district also, there are variabilities within districts as far as COVID-19 prevalence is concerned. So the only way you'll be able to unearth this is to apply the geographic information system supported with the SCAM modeling to be able to get some reasonable guess as to what is going on. Also, delivery of drugs, blood, and other health supplies through drones. Okay, so with the geographic information system, drones are actually programmed to supply drugs, blood, and other health supplies to health facilities or to communities. So what it means is that areas that are even hard to reach, based on geographic information system, we are able to use drones to deliver critical health facilities or health, maybe equipment and other things to health facilities in those areas. For instance, if there's a health facility, maybe due to maybe conflict or maybe flood that human beings cannot get to, maybe no car can access that road and nobody can pass that road to the place. At least if you have a drone, the drone information system, you'll be able to actually supply essential drugs or some blood or other health supplies to those hard to reach communities. These are all based on the idea behind the information systems. And for targeted health interventions, especially in the presence of limited public health, like I discussed earlier, universal intervention is practically impossible. And when this happens, GIS will be very critical to you in prioritizing the little resource that you have. Okay, so what are the systems for the geographic information system that we were discussing? Just like any other modeling or maybe data kind of stuff, for the system to also work, you need a data input and processing. Here we're talking about transformation of special data types. There are different kinds of special data types that you can talk about. So to be able to properly do a good data input and processing, you need to understand the data type that you have. For instance, it could be like topo lines. You want to transform topo lines to elevation data points, or maybe you want to transform lattice data, which is a continuous spatial surface data, into a point data or something. These are all things one needs to understand so that you will be able to apply the technique appropriately, and then we'll be looking at some of them. Also, how do you store and retrieve data in geographic information systems? How do you store and retrieve? Data storage and retrieval is very critical to our work generally, just so it is also in the geographic information systems. We also talk about data manipulation analysis. The analysis component here is also very important, where you can think about modeling, simulations, estimates, and in fact, even processing of the raw data to be able to transform that into a map is also another critical skill that one needs to gather. And for those ones, in terms of the mapping and converting the data from the normal to spatial data set and be able to map it, like I said, we'll be covering that one in the practical session. And just as you do your data reporting and display of information in your usual way, here too, we do the same thing. You know, there are three main ways of summarizing data. You have the tabular representation, you have the local representation, and then you have the numerical representation. But in the spatial aspect, we have the tabular, the graphical, and then the map-based approach, where we insert the numerical data that we obtained. You will see that also. Okay, so in the geospatial data science, we refer to geospatial data, which you can also call geospatial data or geographic information, as a kind of data that references a particular location or geographical area. So if you have a data that is indexed geographically, then you can call that geospatial data or spatial data or geographic information that is acceptable. And then this information could basically be a physical object in a geographic coordinate system. And then we'll be looking at those things as well. Just as we store other forms of data and retrieve them later on for use, geospatial data can also be stored or saved in several formats. And then this can contain more than just a location-specific data. And this is where we say the things like attributes and other objects can be also added. In fact, there are many geospatial data types. However, two main types are identified. We call them geographic data and geometric data. And we'll look at each of these. Actually, it's just a matter of how they are represented. It's just about how they are represented. But they are all geographic data or geospatial data. Now, if you come to the geographic data, here the spatial data is actually mapped around a sphere or the planet Earth. So just as you see if you look at the globe, how the globe looks like, this geographic data approach here try to just present the things as they will look like a globe. And here, this is where we make use of the longitude and then the latitude actually. And we highlight the longitude and latitude relationship to a specific location or object. Those of you who might have used the GPS software before, it's a typical example of the geographic data. That is a global positioning system. It's a typical example. And then when it comes to the geometric data, here, again, the data is mapped on two-dimensional surface. So the first one is usually, we call it 3D, because that one presents the data just as you see the group. The group is presented in a 3D form. So the geographic data, you can say that it is the type of data that's presented in a 3D form. That is fine. When it comes to the geometric one, you can see the type of data is presented in a 2D form. And that's acceptable. Because here we say the spatial data is mapped onto a two-dimensional surface. And actually, it's one of the simplest you can think about in this area of spatial data analysis or science. For example, Google Maps application actually uses this to provide accurate direction. So if you ever use this, your Google Map to get to a destination, then definitely remember that you have used the geometric data aspect of capturing spatial data. There are other techniques we call georeferencing and then geocoding. It's also simply just how you represent your spatial data. You can represent some spatial data just using the coordinates and other stuff, but there are others you have to use what we call maybe geocodes, and these geocodes can be like an ID for a state or maybe a building or district or region. And once that code is mentioned, everybody will know that this is a community or this is a state or this is a region you're talking about. But for georeferencing, typically we're talking about coordinates. So for the georeferencing, here we're talking about assigning data coordinate to vectors of rasters, which support accurate modeling of the planet surface, that is of the Earth's surface. Okay, and then the geocoding, on the other hand, actually deals with providing addresses or location descriptors like information on the district, city, state, countries, among others. The fact is that each of the exact coordinate references a particular location on the Earth's surface, utilizing other address systems or names like district, city, state, or country. That is why even within the geographic positioning system, there are what we call zones. If a zone number is given to you, you can tell which country actually lies within that zone. You can tell. We'll be looking at some examples actually very soon. Yep, Adam, your hand is up.
Yes, please. Good morning, everyone. Yeah, please, I want to find out. So with the geocoding, is it similar or same as the digital address system that we have in Ghana?
Yes, that is the same thing. That's the same thing. So what they did is that they go to areas, capture the area, and assign a code to the area. So if you go to some buildings in Ghana now, you see that they put some numbers on them. So what you see over there is actually typical type of geocoding. That is not georeferencing, that is geocoding. Because once you provide that codes, they can tell which location that person can be located. So that is a geocoding. Is that okay?
Yes, please.
Okay. Now, there are two common, data formats that you can think about. Two common data formats. These are widely used everywhere you go. And those of you who will be developing interest in mapping geographic data and doing some modeling in the near future, these two guys are formats you can never run away from. You can have a raster file that is actually in the form of pixels, and in each pixel, a value is assigned or is present in each pixel. Okay, we call it a raster file. We'll be seeing an example in a practical session. I'll even show you some during this theoretical session. The raster file simply is in the form of pixels, and then in each pixel, there are values assigned in each pixel. But when it comes to the vector is simply how things happen in the real world. So we present data in a vector format, and these are generally created in what you call a shapefile. The vector files are generally created in what you call a shapefile. And then it normally have an extension called .shp. We'll see examples, so don't worry too much. So between raster and vector, this is simply talking about how the data is actually formatted for use. How the data is actually formatted for use. Either it is formatted in the form of raster file or a vector file. We'll look at each of these. Come on, we need to say something. Somebody is saying, please spell, sir. Please, can you explain spell, sir? What are you referring to? Sorry about this one. Somebody send a chat and say, please spell, sir. Okay. Maybe the person is no more here or something. Right. Okay. So the shape file, this is how shapefile. That is how it is spelled, shapefiles. Okay, and then the extension is .shp. That is the extension .shp, and that's a format in which vector data formats especially are actually stored, okay, or formatted. Okay, so like I said, the raster is simply presentation of the data in a pixel grid or pixel form, and with each pixel stored within a raster having what a value. That is basically about it. Like I said, we'll be looking at examples in the practical session, but we provided some examples after, within these theoretical parts. Now, when it comes to the vector here, like I said, it is just how we present this in the real world, okay? That is either pictorially, graphically, with the three main types being polygons, point, and lines. And like I said, they are mostly stored as shapefiles with extension .shp. Now, we'll discuss we earlier discussed about presenting or representing latitude and then longitude under the coordinate systems. So in this session, it's just a summary actually. I mentioned most of this already. Now it's a summary part of it. And one of the, I just told you that you can present the spatial data in a 3D or 2D form, okay? So we are now going to discuss how you present spatial data relating to coordinate systems. First, you have the geographic coordinate systems. Traditionally, this will be the 3D surface. So if you remember the geographic data aspect, you remember what we're talking about. So you can take the geographic coordinate system just like the geographic data we discussed. So this is where you have it in a 3D surface, like how you have the group, okay? And that utilizes the angular unit, that is in degrees, to represent positions on the Earth. That utilizes the angular unit, which is in degrees, to actually represent the positions of the Earth. But when it comes to what we call the projected coordinate system, which we'll also be looking at, you can project a 3D to a 2D surface, okay? So this is what we call the projection systems. You can transform a 3D surface, which is under the geographic coordinate system, to a 2D surface, which will be under projected coordinate systems. So once you transform a 3D to a 2D, here it makes use of linear units like meters or kilometers to represent locations on the Earth. So the 2D is kind of a flat surface, okay? The 2D is kind of a flat surface, while the 3D is kind of the group-like surface, and we'll be seeing it very soon. Okay, so we have the latitude coordinate, which actually index the north-south position of a point on the Earth's surface at any time. And then we also have the same latitude, which measures the angle from the equatorial plane to a given location on the Earth's surface. And this is how comes you're able to tell a distance from one location to another, because distance is involved in these estimations based on the latitude and the longitude. You can estimate distances between two different locations. And the latitude angles range from 0 degrees at the equator to 90 degrees, that is to the north or south at the poles. That's the north or south at the poles. So because as you can see, we're talking about degree. So that is telling you that we are talking about geographic coordinate systems under the latitudes. Then the latitude angles are also measured in degrees, minutes, or seconds, or decimal degrees, the north or south of the equator. So you are seeing some few things down there. In fact, there are 180 degrees of latitude. And then, as you can see, you have the North Pole, the South Pole, then you have the equator. I mean, the North Pole, let me see if this can show. The North Pole is the one at the top here. The arrow pointing to the top here, this is the North Pole side. If you come to the southern part, you have the South Pole here. Then when you go to the right side, you have the east, and then let's say you have the west of it. So given these poles, and then the west and the east, you can tell how far a country will be or location will be from the pole, or how near it will be from the pole. Okay. Then you also have the equator somewhere here, as shown in the arrow. So all these things are very critical in our work. Those who do the purely GIS job, this is what they do. They study this element and they use them to calculate distances and to do a lot of work around spatial analysis. Then the same thing here, but here I try to indicate the degrees, the positions here with their degrees. So each of the positions that you are seeing, those degrees can be used to actually extract information about a country. And if you look at here, 30, we have a 30-degree here. And then these are what you call the zones. So if I talk about zone 30 or zone 31 or zone 32, definitely certain countries will be lying within those zones. So one of the assignment and example that I'll do even from now is to show you, for instance, Ghana or Nigeria or Tanzania or Gambia, which zones they can be found on the latitude and the longitude plane. So the Cartesian plane, that's what you call the X and Y, is simply, if you remember your scatter plot in senior high school, or is it, yeah, I think senior high school, scatter plot, your X is down here and your Y is down here, okay? So your X in the Cartesian plane are actually your longitude, which will be down here. Actually, your longitude should be down here. But your Y in the Cartesian plane will be here, which we call the latitude. That is on the Y axis. So just remember your X and Y axis back in senior high school. And even nowadays, your scatter plot, where you have the Y on the left side and the X down here. So the X down here is the X Cartesian plane, which very soon you see, we call that one the longitude. And then on the left side here, which is a Y Cartesian plane, we call that one the latitude. So very soon you see them. So the decimal degrees are simply indexing the location where you can find a particular country or a particular community or a particular village, okay? So it only becomes meaningful in terms of extraction when you have additional attributes added to that. For instance, you can have let's say a decimal degree of maybe 2 or 3 or something. And on the earth, this is definitely representing an area or a country or a town or a village or just a point, okay? We'll be looking at that. I mean, there's a session on that. So when we get there, we'll discuss more of those things. So now on the longitudes, just as we discussed around the latitude, the longitude also specify the east-west position for points on the Earth's surface. So if I say the east-west, that's moving from the left to the right, okay? We call that one the longitude. So moving from the bottom to the top, that is from the south to the north, that movement on the left side of that is what we are calling as the latitude. But if you're moving from the west to the east, that is from the left to the right, that down there is what we are calling as what? The longitude. And then we say that the longitude also measures the angle between the prime meridian plane and the north-south plane that intersects a location of interest. The prime meridian is actually defined as 0 degrees longitude. The 0 degrees longitude. Longitudes are often given in the form of east and west of the meridian, and that is about 180 degrees in each direction. Just very similar, the presentation is the same for what you do for latitude, just that this is talking about the position, where they're moving from and to where. That's the whole thing. But what you need to remember is when you put this together, you put the longitude and latitude together, then you are getting a point. A single of these is meaningless. unless you put that. If you want to identify a geographical location, you need both the longitude and the latitude to identify a given location. And that is why when you're capturing the data, you always have to get information on the longitude and the latitude values, because it is these two that will index a location. One of them cannot do. Okay, so this is where we converted the geographic coordinate systems, which is in a 3D form, into a 2D form. So as you can see, this one, these are round, like a group. But if you come here, it doesn't look like a group anymore. This is being converted to what we call the 2D form. Okay, this is a 2D now. So here, the lines you are seeing are representing what we call zones. The lines you are seeing are representing what we call zones. So depending on which zone you find yourself, a line can be used. And we all know that the Greenwich Meridian passes through Accra, Ghana. That is Tema. So you see that the 0 here, that is zone 0. You could see that the zone 0 can be seen going through what? That is Ghana. If you look at zone 0, it's going through Ghana. So here, this one is based, we can use the longitude and the latitude values to actually identify a country. That is, which countries lie between certain longitude and the latitude values. Like I said earlier, you will need 2 of these to be able to make a decision about the location. That's both the longitude and then what? The latitude. For instance, if we talk about Ghana, those of you who are good in maps, you can see that Ghana is here. Do you see where my cursor is? Can you see where my cursor is? If you look at the Africa map, Ghana is here. So based on this, I can go to the left side to see which latitude Ghana, on which latitude does Ghana lie, and then I will come down and see which longitude Ghana lies. Okay. So on the right side is what you realize that if you do a thorough check, you realize that Ghana lies between latitudes 4 degrees and then 12 degrees to the north, and then longitudes 4 degrees west and then 2 degrees to the east. If you do a good work, you see that that is what Ghana will represent. So if you want to identify Ghana, all you need is a latitude with degrees 4 and then 12 degrees north, and then you need a longitude also with 4 degrees west and then 2 degrees east. So if you give this information to somebody, the person will be able to locate what? The Ghana for you. Okay. Very soon, you also see the zones. We also use zones to represent countries as well. And then that will be on the next slide. For instance, even Madagascar, which is somewhere here, you can tell that for ease of identification, Madagascar here, it goes beyond -15 small, and then it's also just a little less than -30. And then if you now want to come down, that is a longitude side, you go this way, come down. So that is in between 30 and 60. So if you look in between 30 and 60 for the longitude, you definitely find Madagascar there. And if you look in between, let's say 0 and -30 on the latitude side, you definitely also find what? Madagascar there within that area. Okay, so that's what we do most of the times. But I mean, in our field, you don't have time to be doing this physical inspection. So the software will help us to just extract this within a short time and then map it. I mean, with ease, without any struggle at all. We'll be looking at that in the practical session. So the next thing is the cartographic projections. Okay. So cartography is simply, I mean, let me say, flat or simplified version of geometric representation of the earthward surface. So the one we just saw is a typical example where we transform the 3D to more like the 2D, okay, representation kind of stuff. So that makes it flat. So if you remember, this is very flat. You can see how flat this one is, very flat. But if you look at this one, this is not flat. This is spherical in nature. So converting the spherical to flat is what you call the projections. The projections. So you transform from one state to another. We call it the projections. So cartography is simply made up of a flat, simplified, and conventional geometric representation of the Earth's surface. And then we normally present this in the form of maps, blueprint, or charts, just as you have seen right now. Each representation undergoes some deformations. I mean, this is very important. So the reason is that this is something that is in a 3D form, and we are changing it to what? A 2D form. Again, this is something which is actually spherical, and we are changing out to flat. So definitely some distortion is expected. But trust me, it's still very meaningful, and it does a good representation. It doesn't actually, take away the fact that your area will still be represented accurately. The only distortion is that the way you look at it on the globe, that is on the Earth planet, will not be the same as you look at it when it is flat. That's the whole thing. And then in cartography, there are 3 kinds or types of projections that is available. You can think about a cylindrical, which uses a cylinder as the area of the plane. That uses a cylinder as the area of the plane. You can also talk about the conic aspect, and this one uses a cone as a plane. And the third one, which you call the plane or the azimuthal. Here, no specific plane or tangency area is required. However, normally it uses the poles as a centrality. It uses the pole as a centrality. Yeah, so somebody is saying that, why do we need to change 3D to 2D? Yes, so in some work, it is important that you do the transformations. But when it comes to modeling, you are better off using the 2D compared to the 3D, because in the 3D, you are using degrees, and then in your analysis, sometimes you might suffer some level of accuracy because we want to use real numbers to do the analysis. So very soon, I will show some specific examples as to the need for the convention. For certain analysis, it is important that you do the convention. But some of them, you can still keep it in the longitude and latitude form and then do. For instance, if my interest is just to do some mapping of raw count of data, I might not want to convert to any 2D. Okay, that's still fine. But how about if you have a data from 2 different sources, one of them is in 3D and the other one is in 2D, what do you do? Because there are times in our research field, you might get the data from different sources. And these different sources might capture the data differently. So one of the sources captured the data in 3D and the other one captured it in 2D. And yet you want to combine this data for analysis. Because they're in a different unit, you wouldn't be able to actually, combine them. So you need to convert from one to the other so that you have one unit of measure on which you can do your analysis or the mapping and stuff. So there are genuine reasons for which you have to sometimes convert from 3D to 2D. Okay. If a data set is already in 2Ds, then a third one or second one is in 3D and have to analyze all this jointly, then it's better off converting to the 2D, because even when you're modeling or doing some inference analysis, it's easy to play around with those in 2D than those in 3D. But if it's just a matter of mapping the count or something, and then they are all in 3D, why not? You can remain in 3D and do it. But again, there are critical areas where sometimes you need to convert to one unit so that you can allow much inference to be made. We'll be looking at those things too. Okay, so given these differences in how we will present the data either in 2D or 3D, we can combine or maybe classify maps according to how we combine them, okay, in terms of the projection and the type of property, like the Mercator projection, which looks like the in terms of meters and kilometers rather than the other ones in the form of latitude and longitude. And then the Mercator projection is actually a typical example of the cylindrical projection with each main axis in the northern hemisphere, valuing its size, the countries of that part of the group. So whatever projection you have done, remember that at all times, you want to be able to easily identify locations. That is all about it. You want to easily identify locations. So whatever projection you have done, you have to be sure that it doesn't distort the location of that, assuming if it's a country or maybe a community or a village or just a point, you have to be sure that that projection will not distort the location of those areas you're interested in. I mean, if I say distort, I mean, if I do a projection, that should not move a country which is already identified as Ghana to another location which is earlier identified as Nigeria. So even if you do the projection, Ghana must remain at where Ghana is. Ghana must remain at where Ghana is. But if you have the same data set, but in terms of the projections, one is in the form of longitude and longitude, and the other one is in the form of, let's say, kilometers or meters. When you map them together, there will be a lot of differences. They will not agree because they are in a different unit. So if the interest is to put them together, then you have to convert them to a unit, one unit, which I will earlier explain. So the projections are what I'm showing here. So you have your group, which is spherical on the left side. Okay, this is just like the normal group you have. And you want to project this into another form, which is like a 2D form. Okay, like you're seeing on the right side. So take the screen here to be what you're using to do the projection on this part. Okay, and then when the projection is done, instead of having something like a globe like this, you could have something like this, which is now in a 2D form, very flat. It's now in 2D form. So what we are saying is that there are times where you need to convert the 3D to a 2D. And then I've given reasons why you might sometimes have to do that already. So this is basically what we are referring to as a projection, movement from 3D to 2D. Okay. Naturally, most of the time you have your data in 3D. So if you use your phone to capture or your GPS to capture data, you have it in latitude and longitude, okay? And naturally it will be in a 3D form. But once we have the longitude and latitude values, we don't have a problem at all. We don't need to worry about certain projections. We can just go ahead. If it's just a matter of mapping the raw count, it's not a problem. But if you want to use it for any inferential analysis, where you even have a data from two different sources in a different unit, then you have to do some kind of projection to get them onto the same area. For instance, I can download a shapefile for Ghana, the whole of Ghana, from a website. That might be in a 3D format. Okay. Now, I also gather data or maybe elevation on Ghana, but from another source. But that one, they're using the 2D. For instance, let's say they projected it to, let's say, kilometers or maybe meters. If I want to combine that data with a Ghana map, definitely they will not work because they are in different units. One is in a longitude latitude form, and the other one is in a kilometer or meters form. So you can combine them. They will not work. Okay, so these are some of the reasons why definitely you have to move from one to the other. Map projections are actually used to transform the Earth's 3D surface to a 2D plane. And we earlier discussed that when you are projecting something from that is in a 3D format to a 2D, definitely we expect some distortions. But this is not a distortion that is too high to handle. Okay. And a common projection, which many people, some of you might also know, is what we call the Universal Transverse Mercator, that's UTM, which preserves the location angles and shapes. And the UTM coordinate comprises a zone number, a hemisphere, an eastern and then northern, measured in what? Meters. And of course, these meters can also be converted to kilometers if you want. Okay. So what matters is that you're transforming from a 3D to a 2D. Now, the eastings are referenced from the central meridian of each zone, defined to have a value of 500,000 meters, and northings from the equator. In the north, the equator has northing of 0 meter. In south, the northing have a value of the equator that's around 10 million meters. And there are sister zones. Based on this one, there are sister zones. And each 6 degrees longitude in width. And I'll show you, and you could see, if you look at the right side of the globe here, you could see there are some numbers around it. There are some numbers around it. These numbers are indexing each of the sister zones that we mentioned. And at each of the zones, if you get a zone number, you can tell which country is on that zone, given the zone number. So that is the whole idea of simplifying the whole situation for us. So this is a UTM zone number. So here you can see that we are converted from the globe, that is the spherical nature of the Earth, to a flat surface. And with the flat surface, we have assigned what? Zone numbers. Zone numbers. So for instance, if you want to check which zone Ghana can be located or Nigeria can be located, all you need to do is to ask yourself, where is Nigeria and where is Ghana on the map? So just go and look for Nigeria or Ghana on the map and you get a zone number. Ghana is somewhere here, where my cursor is. This is Ghana, okay? This is Ghana. So if I move up of that, I'll see that Ghana is mostly on the zone 30, because zone 30 is to the left of this thick line. As you can see, zone 30 is to the left of this thick line. That passes through almost ending the right side of Ghana. So Ghana is mostly on zone what? 30. As you can see, this is 30, the whole of display zone. So all country that lies within this space here will be put under what? Zone 30. Okay. So as you can see, Ghana is typically mostly on zone 30. Nigeria is somewhere here. This is Nigeria. This is Nigeria. So you can see that Nigeria is also mostly in zone 32. You can see Nigeria is mostly on zone what? 32. Because this is Nigeria. And part of it is also entering 31. Okay, but majority of it is in 32. And some few part of it is also in what? 33. But mostly you could say that Nigeria is within what? Zone what? 32. Not only look at the greater part of the country where it is falling. The greater part of the country where it is falling. Okay, so that is about using the zones to identify the projected coordinates. So this is actually a projected coordinate system. So you projected from the degrees to UTM form, which is in meters, okay? Now using geographical coordinates, that is a latitude and longitude. The great circle or spherical or geodetic distance, we say this one takes into account the curvature of the surface of the Earth. The curvature of the surface of the Earth, this one takes that into account, which is the longitude and latitude. That's why we have it in degrees, okay? And distance is often given in meters or kilometers the moment we convert from the longitude and then the latitude. We also do what we call the equatorial distance, but this guy does not account for the curvature of the Earth. So this is just looking at the distance between two, maybe locations. Maybe location A to location B, what's the distance between them. And this one doesn't take into account the curvature of the Earth's surface. But this is not a major problem if our study area is small. For instance, I'm doing a study within Ghana. Okay, I'm usually Ghana as a study country. Then I don't have to worry about the curvature of the way the equatorial distance worked. Because if you look at the right side, the red dot that you're seeing, that is how the equatorial distance is calculated, the red dot. It's only measuring the distance between these two locations. That's the red dot. So if there's any curve through which that exists between these two locations, the equidistant distance will avoid that. It will not take that into account, like the blue line. The equidistant distance will not take the blue line into account. It will only take the red line because it gives a straight line. Okay. This is not a problem if the area is very small. For example, if you're doing only a single country or maybe two neighboring countries, it might not be too much a problem. But if you are doing something across the whole of sub-Saharan Africa or the whole world, then in calculating the distance between locations, you need to take into account the curvy nature of the Earth, else your estimate will be biased. So if you are doing a study within a small area, they don't have to worry about the curvy nature of the Earth. But the moment you are doing a study covering a very large geographical area, maybe several countries put together, they have to be worried about not taking into account the curvy nature of the Earth. For example, a country, if I'm doing a study like I said in Ghana, I don't need to worry about the curvy nature of the Earth because it's the same Ghana. But if I'm doing a study between countries like Ghana, Cote d'Ivoire, Sierra Leone, South Africa, Burkina Faso, and all that, then there's a reason to be worried if I don't take into account the curvy nature of the Earth, because that would definitely affect my predictions. Yeah, there's a formula to convert from 3D to 2D. Okay, there's a formula to convert from 2D to 3D to 2D, and then in modeling, we'll do this projection a lot. So you realize that when you do the first mapping, you have the thing displayed like in degrees, which is a longitude and latitude, like maybe 4 degrees northwest of this, that, and that kind of stuff. You see them in the map. But if you do the projection to 2D, you now have them in numbers, like 1 kilometer or 2 kilometers and that kind of stuff. So maybe maybe in the practical session, I will showcase some of those ones in the practical session just for you to be clear about how it is done. It's not a difficult process, but just trying to understand how it works, then how to implement it is what matters. So I think with this question, maybe in the practical session, I might need to put one more exercise and solutions on that. What you have to take also into account here is that if you are doing a modeling, then you need what we call the special covariance function. And in that case, you need the equidistant distances. And this is what we are saying, that if the area is not too big, like just a country, then you don't have to worry about the curvy nature. And you need the equidistant distances to be able to do your work, because distances are what we utilize a lot in spatial analysis, because like the first law of geography, objects similar in space, objects closer in space are more similar than objects far apart. So that's an idea we implement in spatial modeling, which you have to remember all the time. We use that a lot. So that simply means that in generating your distances, you have to make sure you do what is right. If not, that will affect your predictions as well. These are the areas I'm very much concerned with, the projection. So, I mean, I don't know if you have a leader for each of the course. I mean, remind me so that in the practical session, I'll take note and then include one example on that so that you can see how it works in real life. Okay. Equidistant distances are normally used here since this projection already takes the curvature into account. That's the UTM coordinates. And here the distance can be calculated in meters or kilometers. So this is an exercise that you have to do on your own. It's not for marking. You can identify the UTM zone number for Nigeria at your own time, okay? Now, coordinate reference systems and map projections, datums, and all that. Spatial data can be measured or located in the angular unit, which we just discussed, like longitude and latitude, or in a linear unit, which is a flat grid based, which is the east and the north, for instance, in the meters and kilometers. And then it can also be presented in a spherical manner, where you have geographic systems available, which is normally unprojected. You can also call that one the angular presentation. Okay. That's a coordinate reference system. And then you can also have the flat planar, which is so linear. And here, this is actually based on a projected system. And then the UTM2 is there, and many of them. All these are things that you also have to know, but in real work, you might not bother too much about them, but you need to understand that this exists so that in your modeling, those of you who will be going to modeling and stuff, you can remember all this, and then in those areas, you also be well informed as to what to do. In fact, all coordinate reference systems are based on a reference datum. There's a model of the Earth's surface or shape. And in fact, this must be correctly defined, very, very correctly defined for any later projection. Because if you don't do it properly, any later projection might not work properly for you. Okay, so you have to set your coordinate reference systems from day one. So if you get any special data, you need to find out what system of coordinates is this. Then once you know, you can ask yourself whether you want to keep it or you want to change it to another one for your use and stuff. So maybe like I said, maybe do the practical session, we can do something like that. Right. Special data mining and then network processing. This is the same as how you do any work in terms of data mining, or you want to develop some graphs that identify networks in your study. We do the same thing in spatial analysis also. Just that in our own, it is indexed with geographical information or location. So this simply deals with discovering of hidden features or patterns that might be present in a large data set of spatial data. That is basically about what the mining is all about. But it also allows extraction of valuable data on contiguous regions and examine spatial patterns that might be available or present at the time. And this is we're talking about, it can be any data at all, both either in health or finance or economics or something, anything. But here we'll be focusing more on health. Yeah. And then spatial network processing, on the other hand, is simply a graph-based kind of analysis of spatial networks by establishing a linear flow and routine. They are actually normally used to analyze the events that occur on networks or along hot networks. A typical example you'll see very soon. Typically, we have a graph whose nodes are embedded in the metric space. So the more the connection at a particular place, then the more the network around that area, okay, or the more the clustering, okay, meaning that if it's about people, meaning that more people go to that location for a service or something than similar other locations in the study region, that kind of stuff. And this is very critical in our work too, because sometimes, for instance, you want to see how people access health facility within certain region or district, or maybe the idea is to see which of the facilities people access most. Spatially, and you want to find out could a distance be a reason or population be a reason. These are things you can easily do through the network mapping and stuff. Example, you can construct a routable directed graph for spatial network and find the shortest path along a given street in a community. That's a typical example. The whole idea here is to find the shortest path within that community. So you try to map the network across the entire community and see which of them provided the shortest path. Spatial network processing actually is something that is done trying to establish just a route. And here, it's actually a function of distance, to be frank. The network is actually a function of distance between two nodes. And in our work, what we try to do is to allow distance to determine what to work or what did not work. And that is why understanding distance is very important in the spatial analysis. Like I said, the first law of geography said it all, and that is the basis of the cornerstone for spatial analysis. And the distance metric often used to analyze spatial networks is the geographic distance. Example, again, like I mentioned earlier. And then here you have a typical example of what I'm talking about. This is a typical spatial data network processing. So if you look at the group here, this is just like the actual group. You see that maybe should I say nets? It looks like a net connecting things around. You realize that the connection seems to be concentrated around this area compared to a place like this. I mean, there's a lot of concentration around here. Connect. So that tells you that if it's about maybe, like I was saying, maybe access to health care in a given facility or facility across the group, you realize that here people are coming here more to access that service compared to other parts like here. But somebody can also tell you maybe it's because of the number of the people living in that area. But someone can also tell you maybe because of the facility here, maybe they provided a better service or something. But the point of call is, where do they move from before they come here? That's the whole thing. Where do they move from before they come here? Is it that most of them are located within these areas, or some of them move far away? So the network will tell you all those things as to where people are coming from to access the service, that kind of stuff. So these are very critical to our work. And studies that look into understanding the spatial effect or the effect of distance on access to health, most of them do this kind of spatial data network processing so that they can tell if the distance to health facility could be a barrier to access to certain health facilities, as we do. Somebody is talking about ethical considerations as far as spatial data mining and the network process is concerned. Yes, in everything you do, there are special ethical considerations in everything you do. And that is why before you set off your work, you need to seek ethical clearance for your work, for the work to be approved for study. And if they realize that the merit outweigh the demerit, why not? They will allow you to go ahead and do your work. Just make sure that in your application, you minimize any harm that the study may cause. And one of the ways of doing this is to display the locations or the actual locations of the individuals. You can do that. For instance, if I collect information on the information of an individual, I can do a displacement of that location so that the exact location of that person will not be identified. Okay. So we call it displacement. Those of you who are familiar with the demographic and health survey will do that a lot in that survey, where the actual location of the people sampled are displaced. In the urban communities, they are displaced to 2 kilometers. And then in rural communities, they are displaced to 5 kilometers. So that is it. So that is to protect the respondent and to safeguard them as well. So yeah, so there are ethical considerations when you are doing things around spatial analysis. And one way of also appealing to the ethical review board is to let them know that, in fact, the actual location of the respondent will be displaced by certain kilometers or meters so that they cannot be identified. I mean, those are some of the things we do. Yes. Okay. So how do you store spatial data? And what are the theories behind that? You have the hybrid or the ARC info model based on storing a correct type of data in the best place for that purpose and to be used later. And data can also be rejoined when required. The same principle means store only relevant info. That is, for the fact that you can store as many data as you can in the spatial field, doesn't mean that even things that you don't need, you have to keep them or store them. No. All you need to do is to store relevant ones that you think you need in your work. For instance, you can store relevant info in a table of particular feature types, and then also join this at a query or display time. And also you can use the key tables or even numbers to reduce data volumes. Okay, because too much data will require space. and you really want to do things that you don't need. And then we also have what you call the relational databases. These are good for a lot of reasons, and they can also help us to store special data. Many offer special extensions with special analysis functions. Some of them can even help you to do some, just the mapping. Some even go beyond, like trying to help you to do some few kind of default kind of analysis stuff. So they are there. Even in the DHS data, if you go to the DHS website, they have certain programs that they put in place for you to display special hot data. So these are some of the things you have to begin now to explore if you really want to go into this area. And trust me, this is an area, if you go into it, it's always very, very interesting. You have a lot of career ahead of you if you get into this area. I know at the moment it's looking a bit theoretical, but when you get to the practical side, you begin to see things yourself. You appreciate the need for nearly everyone to go into this area. Now, no matter how great you are or how your understanding is about this area, you definitely need tools to work with. You need tools to work with. And the question is, what are these tools? And in the area, because the commercial tools are very expensive in this area, there are a lot of open source tools that you can use free without paying anything. And they are on top as far as open source software is concerned. So in this area, you don't need to pay for any software to be able to do any mapping as far as special data is concerned, no. So we'll look at some of them. Some of them are just for queuing sake, and they have the PostGIS, the MySQL, and they also have the open source DBMS. And these are implemented based on OGC standards. Don't worry too much. I'm just highlighting some of the softwares which are open software. We know with time some of them will become commercial, but for now, they are all open software actually. And many of them. And fortunately, we use some of them, like the RGDAL and Co, how to read a raster file and all that kind of stuff. We'll be doing them in the practical session. So you see how handy these things will be. We also have the OpenStreetMap editor and all that kind of stuff. These are all tools available which are free at the moment. Yeah. Then we have the web also, the web application which we'll be doing now in our practical session. I know you didn't forget. Some examples. This is just to showcase some examples of the special data that we discussed so far. And then let me check my time. 11. So yeah. So some special data that we discussed so far, just to see how in real world things look like. So we are getting there gradually. So we discussed this already, but this is just summary leading to the actual special data type that you can see physically yourself. Data are called special if each of them carries a location and a timestamp. One of the first tasks in analyzing such data is to choose the spatial resolution at which to model it. That is if you want to go into modeling. So somebody will be asking, what's the spatial resolution all about? Okay. For instance, you can produce a map or maybe 100 meter by 100 meter resolution. And that will be among what you classify as a finest map. That is on the most smallest unit. So for instance, if you do 100 by 100 kilometer resolution, what it means is that your pixels or your predictions will be by 100 by 100 meters. That is small. Compared to if you want to do a prediction on a grid of, let's say 5 kilometer by 5 kilometer. So if you want to do a prediction on a grid by 5 kilometer by 5 kilometer, it means your prediction will be every 5 kilometer on the steady region. For example, if it's the whole of Ghana, and I'm doing a prediction and I'm using a resolution of 5 kilometer by 5 kilometer, meaning that I've partitioned the whole of Ghana 5 kilometer by 5 kilometer. That's what I did for the whole of Ghana. Okay. And I'm going to do the prediction according to each of those 5 kilometer resolutions. But if I do the same, if I use the same Ghana, but I'm doing a prediction on 1 kilometer by 1 kilometer resolution, what it means is that I'm partitioning the whole of Ghana according to 1 kilometer resolutions. So the prediction will be at a 1 kilometer level, which is finer. I mean FINER, which is finer compared to that of maybe 5 kilometer by 5 kilometer resolution. And the more localized you want your predictions to be, the smaller the resolution in terms of the number. So if I do 1 kilometer by 1 kilometer resolution, and then 5 kilometer by 5 kilometer resolution, the 1 kilometer by 1 kilometer resolution is expected to be more localized. That is, smaller compared to that of 5 kilometer resolution. And if you really want to make an informed decision on a more localized, like a smaller unit of analysis, as far as your area is concerned, then the smaller the number of resolution. So compare 1 kilometer to 5 kilometer, the 1 kilometer is preferred if you're interested in a more localized kind of a prediction. But if you want more like maybe a more cost, or maybe you just want some kind of idea around maybe 5 kilometer by 5 kilometer prediction, then that would be a more coarser compared to the 1 kilometer. So this is what we refer to as a resolution. So the finer you want the spatial area prediction to be, then the smaller the number for resolution. And then the coarser, then the higher the number for resolution. So if you read some paper that were published on spatial analysis mapping, you see them mention maybe 1 kilometer by 1 kilometer resolution, or 5 kilometer by 5 kilometer resolution, or 10 kilometer by 10 kilometer resolution. Okay, those are some of the things you should know. And one of the first tasks in analyzing such data, like we said, is to choose the spatial resolution at which to model it. And what is the finest possible spatial scale at which inference can be made? Is it 1 kilometer by 1 kilometer, 2 kilometer by 2 kilometer, or maybe 5 kilometer by 5 kilometer resolutions? That one you have to decide it by yourself. The researcher have to decide. But remember that the more finer you want the predictions to, areas to be, then the much smaller the resolution number you want to use. And then, but in doing so, remember that there are computational costs. Remember that there are computational costs. If I'm doing the 1 kilometer by 1 kilometer resolution prediction, the computational cost is higher because I will have more smaller unit to analyze than if I'm doing 5 kilometer by 5 kilometer resolution, because I'll have lesser number of areas to analyze. Okay, so if I'm doing a 5 kilometer by 5 kilometer resolution and the 1 kilometer by 1 kilometer resolution, the 5 kilometer one will be faster for me to, finish or complete the work in terms of computational cost compared to the 1 kilometer by 1 kilometer resolution. Even there are times if you do 1 kilometer, the place is very large. I remember recently I was doing some work for Nigeria, special analysis for Nigeria. Nigeria is a big country. So when I did the 5 kilometer by 5 kilometer resolution, and it works all right, very nicely. It ran within 1 day, I finished with analysis. But when I moved now into 1 kilometer by 1 kilometer resolution, after 1 day, the system just crashed. And the error is that lack of capacity, meaning that my laptop cannot have that computational time or capacity to run that 1 by 1 kilometer resolution. So that's a computational cost also. So sometimes when it happens like that, you need to go and fall on other systems that are in the cloud or something based on what you call the high computers. And then they are the only ones who can help you. But if you don't work with a company that have access to those, sophisticated high performance computers, what do? You have no option that to remain at a much, lesser one than that, like the 5 kilometer by 5 kilometer resolution, because that one worked on my system. But the 1 kilometer refused to work because of capacity. So these are things you need to consider when you want to move from maybe coarser one to the more finer one. The relationship between variables also can be very, very critical to our work, because the resolution can actually enhance or obscure this kind of relationship. So, and like I said, if possible, the more finer, the better, because we really want to use a more localized prediction to inform policy at much smaller units across the country than on a very large coarser level. And in practice, we need to strike a balance between these considerations. Very, very important, else you cannot do your work. So there are, like we discussed earlier, there are 3 main broadly different special types of data. You have the point, reference, or geostatistical data. You have the area or lattice or regional data, and then you have a point process or patterns data. Then this is a typical example of the geostatistical data or point reference data. So this point you're seeing here on the map here, as you can see here, the point you're seeing here, these are the sample locations across the whole of Ghana. Okay, sample location for a survey. This from the Ghana Immigration Health Service 2015, the 2014 one. So here, the point are simply the sample locations. And the colors are representing the prevalence of stunting in those locations. Okay, so the stunting variable here is what we refer to as an attribute in the spatial data. And the locations here, these are the X and Y coordinates, which is the longitude and the latitude coordinate. That's the locations you are seeing. So you could say that each location is now being indexed with an attribute, which is in this case, the stunting variable. So once I get a longitude and latitude coordinate, I can get that location and I can map that location and then also map onto it the attribute, which in this case is stunting prevalence. Okay. So we say that each data point is described by a single non-random point in a map, example, longitude and then latitude coordinates. And then data varies continuously over a fixed region, say region D. Here, the set of point or locations can be survey clusters, as in this case, because in the demographic and health survey, clusters are used. So what you're seeing here, these are cluster locations or enumeration areas. These are not individual respondent locations. These are enumeration areas or clusters being shared by people around that cluster. Okay. Then you can also have the HIV sentinel site or fixed air quality monitoring stations across Ghana or maybe any other country. Okay. What matters is that you have information on the latitude and the longitude, and that any measurement taken from those locations can be mapped onto those ones. That's the whole idea about geoscat data. So here the geoscat data can be binary, discrete, or continuous. Okay. And most common analysis objective is to what? Do prediction. Because you might just don't want to reduce the values at the sample locations sometimes. And generally for intervention purposes, even though data is not coming from all parts of the country, you want to use the information available to you to even make predictions to cover the entire country. Okay. And that is what I've been doing for several years now. You see some examples. So based on the sample locations, data obtained can be, modeled and make a prediction to cover the entire country. So another type which we call the area data or lattice data. Area data or lattice data. So here you have existing predefined boundaries, or maybe you can even create it yourself. You can create a boundary within which each of these belongs. Then for each boundary that is created, you have an attribute for that boundary. Okay, you have attribute for that boundary. So in this case, this is simply the regional polygons of Ghana. So each of these, you can see that there are demarcations for each of the polygons. So each polygon is representing what? A region in Ghana. Okay, and these are currently the 16 regions of Ghana. So here, what we are trying to map here is to look at the cumulative confirmed cases of COVID by region from 12 March 2020 to 17 February 2022. That's what we want to map. Okay, so this map is simply for COVID-19 between the period that I've just mentioned. And you see that for each polygon, there's a color representing the prevalence or incidence of what? COVID-19. Okay. And this is a typical example of what? An aerial data. But this is not what you get originally. Originally, you only have the shapefile for the regions of Ghana standing somewhere. And you also have the data set standing somewhere. That's, for instance, in this case, you have a data on COVID-19 standing somewhere. So you, as a geospatial technician or maybe expert, you now have to combine these two data sources, the location data and then the incidence data, that is the COVID-19 data. Then you need to now make these two data sets together. And then from there, you now be able to map them. Okay. I've done this mapping. This is a static one you're seeing, but what you're seeing here is the web-based version. So like I told you, we move from the static and then to the web-based. So what I put here is a web-based version of this map. Okay. So if I go off from the PowerPoint presentation right now, I'll be able to show the web-based version of this very map that you can clearly see. So let's see how it goes. I have to move away from the PowerPoint presentation mode. Okay, so all I need to do is to click on this icon here, which I have built based on the mapping. So if I click on this, it will give me a signal either I want to open this or not. This is for security reasons. You can allow it or you don't. If you're not sure, you can decide not to allow it. So for me, I want to allow it. So let's see how it goes. Currently, I think I'm only showing my screen, but not the entire distance. So let me see if I can reshare the. Reshare. Let me stop this and reshare. So that I will share the entire screen rather. Share screen. Okay. Please, can you confirm if you are still seeing my screen?
Yes, sir, we can see.
Yes, we can.
Okay, so all I need to do, okay, let me start again. All I need to do is to click on this guy and it's asking me if I'm happy to open. I say, yes, I trust the system, so open it. So can you see the current screen?
Yes, please.
Okay, so this is the this is the interactive web-based map I'm talking about. And if God permits, we'll be able to do something like this before we finish the course. So I can zoom out. If those of you are not familiar with Ghana, you can zoom out and see some features. So you see that if I'm giving a static map, it will not tell you that there are rivers around these lines. You see, these are rivers, okay? These are rivers or lakes, okay? But if I give the static map, you don't know that these are all hot rivers or something. Okay, so you might be right, you might be thinking of doing intervention around these areas, and in fact, it's a river. Okay, and there's a more reason we need to move beyond the static maps. Okay, even sometimes if this were to be at the individual level, you see the COVID seems to be higher. See, the deeper the red, the higher the prevalence of or the incidence of COVID. So here, this is Greater Accra region, recording the highest prevalence or incidence. If you come to the next one, is what this Ashanti region. So what I try to do is that I tell the student that whatever I mapped, bring the name of the region if I put a cursor there, and also bring the number of confirmed cases if I put a cursor there. So this is telling you that this Ashanti region, look at the name, and it's giving the cumulative confirmed cases as well. So as at the period we're looking at, Ashanti region recorded 22,286 confirmed cases for COVID-19. So this one, if you are a policy decision maker and I give you a map like this, all you need to do is to put your cursor around these regions and see which of them is having the higher or the lower cases of COVID-19. That's all you need to do. But if I give you a static map, somebody even looking at the colors and relating the colors to the figure that is here in the key is difficult for the person. But you put a cursor on it, it gives you everything. So what do you need? That is all. I know that this is Greater Accra and number of cumulative confirmed cases, 88,425, as at the time you're looking at. Okay. But if you look at the static map that I show you in the PowerPoint presentation, you wouldn't be able to get this data. No, it's not possible. Even this at the regional level, we can even do this at the district level. Okay. In fact, we can even do this at the individual cluster levels. So if you see some of my published works already online, these are some of the things I've been to for several years now. So we're moving away from the static maps to interactive web-based maps, whereby just pressing a common cursor on your map at a particular location, it gives you what the cases are and the name of the location. In fact, even some of us Ghanaians, not of us are good geographers. If I ask somebody in Ghana around, okay, this polygon, what's the name of this region? They cannot tell you. But the moment I put a common cursor on it, it gives you the name of the region and the number of cases in that region. So these are some of the things we want you to do. Unfortunately, we'll be covering this before the end of the course. So I expect many of you to develop interest in some of these things, because this, even at the regional level, you can even do this at the district level once you have a data at the district level, no problem at all. You can do the same thing at the individual sample levels. Once data is there, you have no problem at all. All you need is an information on the geographic data and then an information on your survey data. You combine them, you are good to go. Okay. There's a question here. How to do if some area unit needs data for the region of interest? Yeah, so you just, there's a way we code them. If you have, for instance, let's say if you have this region, Ashanti region, it's not having a data, you just leave it as it is. When you finish the mapping, we are normally assign a code of not available to it. So you tell the system, they will ask you, how do you want to name missing data? you can just write it maybe missing data or not available. That is fine. So it's not a big issue at all, because in many situations, there are situations whereby you might not have a data for certain locations. For instance, like I said, if we went to have a data, we just assign it to missing data or maybe not available. And then in your key, you see it in your key here. It will be added to the key here. So you see another color for not missing in your analysis. So it's not a problem at all. Okay, so please let's go quickly. I intended to wrap up earlier, but it looks like but it's good I showed this. So let's go on now to finish up. The remaining ones I'll just run through quickly because I discussed this already, but I'm now showing you the real, the practical part of it. What I've discussed with you, I'm just showing you the types and how they looks like and what you can do and stuff. So please don't worry. I programmed myself to finish the first session at 11 o'clock Ghana time. So I think I'm on course. Then we can start with the practical. Right, so we are still on the data types, okay? So these are aerial data or lattice data. Okay. Then we also have to call the point patterns. Point patterns. So here, this is a typical example of point pattern data. And in 1854, there's this gentleman called John Snow. There happened to be a very strange disease killing a lot of people in London. Many attributed this disease to activity of witchcraft, wizards, and all that. Then there's this epidemiologist, whose name I just mentioned, John Snow. He believed that no, the disease cannot just be strange like that, and that there should be an underlying cause for that disease. So he decided to map the location of where those who are having areas where people are reporting the outbreak of the disease. He decided to map those areas to see what is happening. So when you hear about certain case in a particular area, you go to the area and collect the data and map it. So along the line, it's coming up that there is a particular area where people are getting more infected of the outbreak. But then the name of the disease is not even known. It came clear that there's a particular area where number of people who are actually, getting infected, the number is so high. So he decided to go to that area to see exactly what would be the reason for that situation. And when he got there, he realized that that is an area surrounded with a pump, that is water pump. That is an area surrounded with water pump. So if you see where my cursor is, you see that there's a lot of thicker or bigger red areas here compared to all other areas in London where the infection is taking place. So without even testing the water or anything from this pump, John Snow believes that no, the strange disease that they're talking about might not be about witchcraft or wizards or anything, but he could take away the handle of this pump here to see what happened to the prevalence or the incidence of the disease in this community that's in London. So John Snow just removed the handle of this pump, and that leads to the end of the strange disease that was affecting people in that area. Okay, so no intervention. The only intervention he did is to map what? The number of people who actually are infected, and he got to know that, in fact, more cases are reported around this very pump here, and the only intervention he did was remove the handle of the pump, and that is the end of the story. The infection went down and stopped completely. And since then, they give the name of that infection or disease as what? Cholera. Cholera. So this is how the name cholera actually came about. So they realized that the water here in this very pump is so contaminated. That's the decision they arrived at. They realized that the water coming from this very pump is contaminated. So anybody who come around here to fetch this water will be infected with the disease. And that disease today is what we are calling as cholera. So this is a typical type of what? A point patterns data. Okay. So here you just want to find out why things are clustered in space. And you index that with a point. And that is what he has done. So here we say data occurs at a random location So the domain D, where the data can occur, is random. It changes with each realization. So anytime new data is available, it changes, the size of it changes. There can be explanatory variables to also explain the observed pattern of points. Examples include the location at which weed emerges in a garden, occurrence of disease outbreaks, like I've just explained to you, and lightning strikes, among others. Analysis objective focuses on determining the pattern in the observed data, example, clustering, as I've earlier mentioned. Okay, so somebody is saying it's expecting an example of this case. Okay, no problem. Once time we allow this on the problem at all, we can explore. Yeah. I even have some typical examples from that already, so don't worry. Okay, so we discussed this already. So this is just a recap again about data types. We said there are, for the vector type, there are three main ones. We have the point, and then lines and polygons. Okay. And then when it comes to the raster file, earlier we discussed that these are actually captured like pieces in a pieces grid. And for each grid, there's a value assigned to it. Example, you can think about elevation or altitude. You can think about the pH measurement. You can think about stunting at a particular location. These are all can be all this can be captured in a raster format and then displayed. We'll see for this. We'll see some example. Even how to read a raster file and display it in a map. We have examples to do in a practical session, so don't worry. For the attribute, we talk about this already as just like properties that you can capture for this. We have it for both the vertex and also for raster, so don't worry too much. What are some of the GIS tools? I've listed a lot of the GIS tools that we use in geospatial mapping, visualization, even the modeling and other stuff. But like I said, for this particular course now, we are only going to do the mapping part of it, no much into modeling. But these are all softwares that can help you to map. Some of them can help you to do the model. And for each of them, I've provided what they can do for you. Okay. So you have something for the base data manipulation, something for cartography and data visualization, something for spatial analysis. So under each of these, you can familiarize yourself with what each of these can do. And then, of course, some other softwares. And then we discussed these ones earlier, but I decided to bring these ones at your level. These ones are things you can easily work it without a struggle. Yeah, so in our practical session, we'll be looking at some data from Ghana also, and I think from Nigeria, and also from one other Africa country, just to explore the environment. And then they'll be very helpful to our work. And how do you store spatial data? We discussed this earlier, but this is just a pictorial representation of some of them. In the real world data, you have attributes stored as polygons or as lines, or maybe as any other thing. And then when it comes to the raster file also, you have pixels. So each of these squares represents a pixel. And in each pixel, you have information. For instance, if you look at this pixel, there's an information called R. Maybe this R could be a value like maybe 2, 3, or anything. Or sometimes it can just be a variable, a letter like this. Maybe R represents a rural community, that kind of stuff. Meaning that this attribute here is representing that this grid here is from a rural community. Because sometimes you can take this as an exposure variable, which you call independent variable in your modeling. So you can do that. You can even map for instance, you can have a regional map or maybe district map, and then you want to see where rural and urban communities are located within each of those districts. You can map it, it's easy. And then the vector, of course, you can also do the same. Right, for the outcomes, I think we'll be considering, in the practical session, we'll be considering stunting, wasting, underweight. Then we'll be considering skill of attendance. I think that one is in Nigeria, but the stunting I think is in Ghana. Then the vaccination also I think is in Ghana or maybe some other part, something like that. So, but what matters is that we need the art to be able to combine those data sets and they use and they map them. Yeah. And it's always good practice to understand the definition of the variable to be modeled. You have to be familiar with how the variable is coded in a data file. There's either it is continuous or discrete or categorical, we need to know. And you may also need to do some data cleaning and imputation. There are times you might have a very important variable in the data that you want to use in your final analysis, but it might have some few missing observations. Yes, you can still do imputation before you do the actual modeling and stuff, so it's still allowed. And then most of the time, the data needed for model fitting will only include number of individual samples from the survey cluster, and the number of individual who possesses the attribute being modeled. And there are other times you can have individual level observation, like, but these are not very common. Like if you are doing a study across the whole of Ghana, it's difficult to collect information on the individual respondent to location. Maybe sometimes the household location of the individual is fine, but it will cost a lot to gather, geographic data on all households in Ghana, or maybe a good amount of sample households in Ghana. And that is why even in the demographic health survey, they have to use a cluster. That's an enumeration area for data gathering. And that's why we say most of the time you have a data of a number of people sharing a particular location, like a cluster. Yeah. So this is a typical example. So I have an ID. This is a common Excel file that I created. Okay. So when I collect data, I just enter it to Excel file. So I have an ID for that respondent. I have total number of people sampled from that location. I have a number of people who have achieved this vaccination. So I have a number of people who are vaccinated from that location. So for this one, the first person with ID number 1 is a community. So yeah, the unit analysis is now a community, which we call a cluster. So meaning that from this cluster, 7 people are sampled from that cluster. That children are 5 are sampled from that cluster. And then out of the 7 samples from that cluster, 5 of them receive vaccination. That's basically about it. So here, if I want the prevalence of vaccination of vaccinated children at cluster 1, it's simply 5/7. We call it the naive prevalence. Okay, and I can map that prevalence. I will do the same for all the other clusters and then map that prevalence across the study location. And in fact, just as what you saw in the map I presented earlier, where I was talking about stunting, similar. Okay, then here, this is where we have the guys. This for the latitude coordinate and then the longitude coordinate. And like I said, if you put the two together, you get a location. So meaning that for the first cluster, the latitude is 7.7 something and the longitude is 8 point something. Okay, and you do that across the whole sample, the cluster that you are going to use. And once you have this information, even with this information, I can create additional column, which is for the prevalence at each of the sample locations. So I can create another column and call it prevalence or vaccination prevalence, which will simply be me dividing the vaccination count at each cluster by total number of sample children at each cluster. That's all. And I'll put in that column and I'll do it for all the other ones here. So once the job is done, I can now convert this into a special data. Currently, it's not a special data, it's just normal data frame. If you read this into R or any software, it will just be a normal data frame. Then you need to convert this into a special data. We even have softwares that can help you to map directly from a data frame into a special map. Okay, we will be doing all those things in a practical session, so don't worry at all. We'll be covering all these things. So I've shown you this before. So here I use a longitude and latitude to get a location, and I'll get a prevalence at that location, and then I'll map it. Just this. Okay, so nothing to worry about. And also, these are normally obtained from various sources. Yeah, I mean, you can get this data from a lot of sources. Like if you want to go into modeling, you don't just model the count or the observed outcome. You want to also use some variables to explain those outcomes. Like if you are getting some outcomes, you might want to ask yourself, what variables might, explain some of these outcomes that you are realizing or that you're observing in your study. For instance, could it be that maybe the presence of stunting could be influenced by maybe travel time to urban areas, or maybe night light intensity, or maybe average precipitation or vegetation index, or maybe if you have a data on poverty at that geographical level, which you call poverty index, or maybe if you have a data on a livestock index, how are they playing, or altitude or elevation? How are they influencing the outcome? You might want to account for this so that you can explain if you are getting some variability in your data or your outcome, you want to explain what might be causing those variability, okay? And normally we encourage people to use what you call the geospatial level covariate, and these ones are indexed geographically. Those are what you want. Not if you want to do the individual level data, it's also okay, but there's a lot of uncertainties or maybe other things around that as well, because in the spatial analysis, we're interested in the effect at geographical level, not at the individual respondent level. But some school of thought also argue that you can start from the individual level and then aggregate at that higher level so that you take into account all the variability. But there are other ways you can do that in the modeling, because after taking care of the spatial effect, you could allow for random effect at the individual level. So that also takes into account the variability at that individual level. But any way you do, all is fine. Okay, so we have demographic variable, remoteness, climate, environment. So these are just some geospatial sources of gathering data. And then sometimes you don't need to have this data coming with the outcome variable, because if I have a location that has the longitude and latitude coordinate, and I know the year that the survey was done, and they don't have this geospatial covariate, I can make reference to that year using that longitude and latitude coordinate to extract the value at those locations and add it to the survey data. Okay, so sometimes some people will tell you that, oh, the survey didn't come with any geospatial covariate, it's only the individual ones there and there. That shouldn't be an excuse at all. Where we are right now, we have the softwares and other things that can help you to even extract the geospatial data covariate that is currently not available in the survey and add it onto the survey for your work. Okay, so this is just to showcase what we call the geospatial covariate. So each of these layers on the right side here are indexing different geographical covariate. Maybe the first one could be like vegetation cover or index. Maybe this could be like precipitation. This could be like altitude. This could be like maybe poverty index. This could be like geographical covariate. Maybe let's say things to do with light intensity or temperature or something. So take each of these to be a layer that we can extract relevant geospatial covariate from. Okay, so as you can see, these are looking like a raster files. These are looking like a raster file. So we can, at each location that we have the longitude and latitude, we can extract any value at that location from here and add it onto the survey data, and they use that in our modeling and prediction. Easy. So like I said, the resolutions can be at around maybe 1 kilometer by 1 kilometer resolution, or 5 kilometer by 5 kilometer resolution, or 10 kilometer by 10 kilometer resolution. Any of them is fine, depending on your interest. And like I said, for policy decisions and to be at optimal level, it's always interesting if your system can support 1 kilometer by 1 kilometer of resolution. If I say support, I'm talking in terms of computational costs. Yeah, so I explained this already, that for instance, the DHS have a data displacement policy. So in the urban communities, they do it to 2 kilometer displacement, and then in rural, they do it to 5 kilometer displacement. This is simply to protect the identity of the respondent. That is all about it. And another typical example of the geospatial covariate, as you can see, this livestock density, urbanicity, but the urbanicity here is just yes or no situation. If it's urban, 1, if it's not urban, 0, which means urban and rural. So rural is 0, urban is 1. Then the night intensity, proximity to national borders, they have the longitude and the latitude. So if I have this data, because I now have longitude and latitude here, just as in the other one, it's easy for me to match, and I'm gone. Someone is asking if I can give a source where you can get a daily temperature at country level in Africa from 2020 to 2022. There are many of those sources. If you go to the MODIS site, MODIS, site, they have a historical data and all these things, temperature, elevation, vegetation index, and all that. So just Google MODIS, MODIS, and then there's this all over the place there. You can get even as far back 1960s or 50s and stuff. You can even get it on maybe monthly basis or yearly basis or any way you want. Yeah. Okay, so the interpolation. So I explained earlier that given these samples taken from these locations only, you can develop a modeling framework that you can do predictions to cover the entire Ghana, which is this one. So this is a work that I already done, which is published already in Malaria Journal. Another part of this also published in the Lancet Journal. You can go and have a look at it and then have some interest. So from here, you develop a special model, and then you do your estimation, you do your prediction based on that model to cover the entire Ghana, and then you are here. So you move from the left side to the right side. Okay. And also, this is also based on the special application and the web-based mapping. So let's go again and see how it looks like. So here, this is just the naive, we call this one the naive prevalence. So you have the sample location with the naive prevalence, as you can see. So I can open this one again and showcase for you how it looks like. So you see this one, I can zoom out, and the more I zoom out, the more you begin to see smaller towns in Ghana. Is that not it? I'm here now. You are not able to see that there are smaller towns in Ghana. The moment I zoom out, you begin to see that there are a lot of smaller towns showing up. Is that not it? For instance, if you come to, let's go to Accra side. We are around Accra here. This is Accra, okay? This is Greater Accra here. We are in Accra here. So you can zoom out and see even more smaller towns like Kokumemre, Kanda, La, Bamaka, Teshi, and all that, okay? So here you can tell if this is green, you can tell what the green is representing. This is Kanda, this one is around Kanda. So if you within Kanda, you can zoom out and see specific smaller area where this point is taken from, okay? By the way, this is internet dependent. You need to have internet to see these things. If you don't have internet, it will show it to you, but it will not show you the towns, okay? But if you have internet, it will show you the towns where this is coming from. So with this point, I mean, I know what the whole system is talking about. So you can see the demarcations, the houses and stuff, how they are structured across Ghana. This is the beauty of the interactive web-based map. So anytime you want to find out what's happening in those areas, just a matter of going down onto the map and trying to see where these areas belong, and that's it. Okay. So that's about this one. So on this note, we can now go, now using this information here, together with environmental or geospatial covariate, I was able to develop a map, which is this one on the right side, to cover the whole of Ghana. And this is telling me that children coming from the northern part of the country are more stunted. But this is a static map, so this, I cannot read, I only know this is another region. But which towns are able to show more in terms of stunting prevalence? We did another region. Even though it is not uniform across the country, at least it is very high here in another region. So that will lead me to also open up what I've created for the predicted prevalence across the whole of the region. So you are here now. So as you can see, this Tamale, you can see another region. So I want to zoom out to see which towns are around this deeper red where the risk of stunting is very high after the modeling. So this is not just the mapping. You have the naive prevalence positions. Now you adjust for special or the special covariate to fit a special model. Then after fitting the special model, you do your estimation and the prediction. Then you now develop a web-based system that supports your prediction so that when you open your predictions, you can interactively engage with the map, okay? So three things in one. First, you get your survey data with the geospatial information in there. Then you fit your model. Then based on the fitted model, you do a prediction. Based on the prediction, you do your map. Then after doing your map, you develop an app based on the same map to interactively engage with the map. So these are the steps involved. So right now, this is where we are now. So if I zoom out, you could see that we begin to see smaller towns coming up. I can see something like Zabzugu here, Tatale here, see something like Saboba here, Saboba district. Like if you come there, you can see something like Kwabe here, something like this, they say Tamale metropolitan. So here we have something like Tichili, Pagaza, then Chagnayili, and all these things. These are things you cannot see in the static map. Something like Futa, and you could see that these areas are showing red, meaning that these are the areas in the northern part of the country where the price of something is very high. You can see things like Kwandele, you can see things like Fuel. They are all located within the high risk areas. Something like Bong or the Chambulugu. These are things I don't know anything about. But based on this procedure of developing the web-based map, rather than the static one, I can now tell where these areas are. And if, because you don't have the resource to roll out intervention to cover everybody in another region, the little resource Ghana is having, we can go to these red areas and then roll out the intervention for them, because they are the one at the most need at the moment. Okay, so here the spatial analysis and web-based narrative aspect is helping you to identify communities where the risk is high and they need urgent intervention. And then the areas where the risk is not high, you need to learn from those areas. For instance, if you look at this area like this, around Mole National Park, they don't appear to show high risk of stunting prevalence. So one good thing a policymaker will do is to go to those areas to learn about why they are not picking up a high risk of stunting. Then you can transfer that idea to the high risk areas like these ones. Okay, so this kind of application helps you in two ways: identify high spot regions or communities for urgent intervention, and where the risk is low, go and learn from there as to where they are getting low in terms of the risk, and you transfer that idea to where there's a high risk. That's it. Okay. Okay, so someone is asking what is the exact title? Do you use kriging? Okay, so what is kriging? Kriging is simply an interpolation procedure. Okay, that is you have observation for certain parts, and then you don't have observation for certain parts, but you want to be able to produce an estimate that can also cover the entire study region. That is just about kriging. Interpolation and kriging are the same thing, but this is based on a mathematical modeling approach. Okay, kriging and interpolation, they are the same. Okay, interpolation simply means that you want to move from one area to another. You have something, you don't have something, you want to put something there. That's it. Kriging is just a prediction. And you and I know that if you don't have something for something, and you're able to get something for that place, it's a prediction. You are predicting for that area. So if you look at the left side map, you could tell that it's not every part in Ghana that we have data on. But if you look at the second side, we have now gotten prediction for the entire country. So that is prediction. Kriging simply means prediction, and interpolation is similar to that. Okay, let's wrap up. I think, yeah, I'm beyond my scope now. It's 11:13 instead of 11. Okay, so that is it. So this is an idea we want you to buy into and then endeavor to get into the field. It's very, very interesting. And there's always a lot of opportunity out there waiting for you guys. Some of us were in the field here. We really don't have time for ourselves now. Every now and then we are on the move. And what you enjoy here is that this can be applied in any field at all. Any field, this can be applied in any field. You don't have a limit. Either in economics, finance, health, agriculture, everywhere. Everywhere. Okay, so just as we do predictions, you also have to take into account the uncertainties around your predictions. In fact, no prediction is exact, okay? In life, no process is exact. So once you know about this, when you are predicting, you need to take into account the uncertainties around your prediction. So here, I just repeated my prediction that I showed you earlier. That's a predicted stunting prevalence. Then on the right side, I showed you the standard error for that prevalence. And the minimum we have here is about 0.01 or 0.02, and the maximum is about 0.09 in terms of standard error. Very relatively small standard errors. So this is telling you that the uncertainty around the estimate is very small, meaning high reliability, or maybe the precision is relatively high. if you look at the standard error relative to the predictions, this is good to go. So meaning that we have reliable estimate that we can rely on for our decision making. That's the meaning. So anytime I tell you produce some work and you produce some estimate or predictions, remember to always attach the uncertainty around that prediction. In fact, if you like, can you do the width of the 95% confidence interval rather than the standard error, so that you can look at the worst scenario and the best scenario around your estimate. That is also very fine. Okay, so I want to acknowledge some few people because these are some people who are also in the area. For those of you interested, you can read about them. And then I think the next one will be the practical session. And with the practical session, these are the things I'm interested in. Searching and downloading data from sources, preparing and mapping the data, using leaflet, TMAP plot, and then SP plot functions to map the data, and creating static and web-based maps. So these are the areas we'll be covering in a practical session, but we'll be using real-life data so that you can see physically how even you can also start to do some of these things on your own when you go back to wherever you are, your offices. On that note, I can only say a big thank you for the first session.